Muy buenas tardes, tengan todos ustedes. Vamos a iniciar con esta conferencia titulada de la ductilidad, la reparabilidad, que nos dará el doctor Ken Elwood. Quisiera yo brevemente presentar, a varios de ustedes ya lo presenté hoy en la mañana que tuve reunión con varios de los estudiantes, pues el doctor Ken Elwood es una de las autoridades jóvenes de la ingeniería sísmica a nivel internacional, y para el Instituto de Ingeniería, nosotros en México nos da mucho gusto que tenga la oportunidad de visitarnos. Esta es la quinta ocasión que viene a México. El doctor Ken Elwood es canadiense, estudió en Canadá su licenciatura, hizo su doctorado en la Universidad de California en Berkeley y posteriormente fue contratado en la Universidad de Columbia Británica como profesor. De ahí fue seducido por la Universidad de Auckland en Nueva Zelanda. Recuerden ustedes que Nueva Zelanda es uno de los países sísmicos más activos sísmicamente, con una escuela muy robusta en ingeniería sísmica, probablemente los 3 profesores más conocidos por todos, el profesor Park, el profesor Polley y el profesor Plistri, lamentablemente los 3 ya fallecidos, que impulsaron de manera muy activa los conceptos de diseño por capacidad y el diseño por comportamiento, con un comportamiento dúctil, con un detallado muy cuidadoso de los elementos de concreto. Bueno, pues ahora Ken viene a reforzar a las generaciones más jóvenes en las universidades de Nueva Zelanda, y él va a explicar un rol adicional que tiene en el ámbito de la ingeniería práctica en Nueva Zelanda. Entonces, afortunadamente, su estancia en San Francisco le permitió venir ahora. Tuvimos la reunión de convención del Instituto Americano del Concreto para darnos esta conferencia que forma parte del ciclo de conferencias de conferencistas distinguidos de la Sociedad Americana de Ingeniería Sísmica, el ERI, y que pues dan a diferentes capítulos en diferentes partes del mundo, en este caso al capítulo del ERI en el Instituto de Ingeniería, y que es coorganizada esta conferencia por los capítulos de estudiantiles de las Sociedades Mexicanas de Ingeniería Estructural y de Ingeniería Sísmica. Así es que, Ken, como siempre, muy bienvenido, muchas gracias por darte el tiempo para estar con nosotros, y te escucharemos con mucho interés. Thank you very much.
Thank you, Sergio. I said very nice. Thank you, Sergio. I did not understand much of that, but I did hear the names of Park, Pauley, and Priestley being listed, and I do not feel my name should be listed in with such great company. But it is truly an honor to be here and to be here representing New Zealand, representing ERI, and so I thank you for the invitation. And I first want to note, I do not have a typo on this slide. This is the 2022 ERI Distinguished Lecture. It just so happens that with COVID and the rest of it, ERI has encouraged me to continue to give this talk for within as in 2023. But next week, or actually this week, in San Francisco is the ERI annual meeting, and we will be hearing the 2023 ERI Distinguished Lecture at that annual meeting. So thank you again, and I first want to start off by saying that my personal role has changed since the time I got this invitation to give this talk. In fact, just by coincidence, the same week that I was invited to give this talk by ERI, I was offered a position in the New Zealand government, essentially as an advisor to two organizations. These organizations are the Building Performance Branch of the Ministry for Business, Innovation and Employment. This is essentially the building regulator, if you will, for New Zealand. They're responsible for maintaining and the building code, as well as Tokatuake EQC. EQC is the public insurance agency for all residential homes in New Zealand insurance for natural disasters. So they're interested in supporting further understanding of the performance of residential buildings in earthquakes. And they partnered with the building regulator to develop this position of a sort of an advisor, if you will, in the building resilience space. And I find it fascinating because I've always worked in this space between research and practice. I've always been driven by that connection of my research to being implemented in practice. But this position allows me to connect in with that nebulous entity known as policy. And we really can't achieve all that we want to achieve for seismic risk reduction unless we influence policy. So I'm honored to have the opportunity to sit in this role. And this triangle that connects the three can be represented by what we call our building regulatory triangle in New Zealand. At the top, we have the Building Act, the legislation that tells us that we must build safe buildings. The building code sits underneath that, which defines very high-level performance objectives for those buildings. And then a set of means by which you show compliance to that building code. The most common means of showing compliance is what is called here verification methods. These are your standards. The ACI 318, for instance, would be a standard that is used perhaps not in New Zealand. We have NZS 3101, but it would be cited within a verification method. You also have acceptable solutions, which are simple means of showing compliance for simple structures. And then you have alternative solutions over here, which are much more complex, where you have to demonstrate that you show compliance with the building code. And so really, much of my work involves advising how these get developed. And it couldn't be a coincidence that I was invited to give a talk for ERI about earthquake resilience on the same day that I accepted a position like this. And so I thought maybe I could use this as an opportunity to dream about where I see these pieces. And in particular, I'm going to talk about with the verification method piece, that those standards that we use all the time as engineers, where I see those maybe going in the future as a way of dreaming about where New Zealand might go in the future. But I must emphasize in all of this, these are just the crazy musings of a professor, not New Zealand government policy. Might be someday, but at current time, these are just my ideas I want to share with you. So before I get into it, of course, I must thank all of those who supported me to be here. I've already mentioned ERI, of course. All of my graduate students, as the professors in the room here know, we can do nothing without your support and strong and good work. So I very much appreciate all of my graduate students. But in particular, I want to shout out to Ann Halsey and Tayo Opabola, who are two postdocs whose names you will see show up on many of the slides here, because they really put in the hard work to make this lecture possible. And I've talked about this as I've developed this lecture with many colleagues, and I've appreciated all of their input along the way. In particular, I want to thank an ATC project team, ATC 145. This is a project that is developing guidelines for the repair of earthquake-damaged buildings. And I've used a lot of the ideas that have come from this repair guide, but sort of flipped them around and said, how can we design to be repairable in the first place? And of course, I have to thank all the funding agencies that have supported me through the years. All right. So why are we here? What's my objective here? Well, I want to, as I said at the outset, I want to focus on sort of code minimum building design in light of what we've seen from recent earthquakes. And there's a lot that goes into that into that code minimum. I'm going to focus on the design loads and deformation limits. But there are many other aspects to the code that are as or maybe even more important, perhaps, than these limits. But those are the ones I'm going to focus on here today. And in developing these possible changes, I want to make sure we think about a few things. First of all, we need to recognize the inherent uncertainties in seismic performance. Okay, uncertainties in the earthquake, uncertainties in the performance of the building, uncertainties in our ability to predict that performance. Okay, that's going to be a critical thread I want to draw throughout this. I also want, even though those uncertainties make it complex, I want the implementation to be as simple as possible. Otherwise, it's not going to get into the code, right? So I want it to be as simple as possible, but no simpler, because we are dealing with a complex phenomenon of the performance of buildings to earthquakes. We need to recognize that. Okay, so you need to make that balance. And I want this to actually be a relatively small increment of change. And you might say to me, well, you have an opportunity to dream big. Why are you making it small? Well, I think a small increment of change has the greatest chance of actually being implemented, right? And so if we can still have positive impact and significant impact, but with a small increment of change in how we design buildings, that to me is it's going to be a strong argument for the change. And then finally, I want to demonstrate to you that I think many modern buildings today are already repairable after a design level earthquake. Okay? And I'll try to demonstrate this with a couple of case studies. But if this is true, that really gets us a long way to saying, yes, we can design repairable buildings. Okay. So first, let's think about what I'm going to call the building design improvement cycle. Okay, and in the good old days, this would essentially be triggered by an earthquake happening, and then we go out and we look at the performance of these buildings, and we probably spend most of our time when looking at those buildings focused on the structure, right? Non-structure may be damaged, but our focus was on the structure. A lot of this learning, by the way, came through the ERI program, Learning from Earthquakes. So hats off to that program for all the learning that has gone on. And after Learning from Earthquakes reports back, we ask ourselves, okay, what sort of changes do we need to make in the design of our buildings to improve that structural performance that we've observed? And it's really out of process that our ductility-based design principles of today were born. And a lot of these were embodied in the key document ATC3, which is really the foundation of most modern seismic design codes around the world. And I think the poster child for this was the San Fernando earthquake that affected the Los Angeles area. This, of course, being Olive View Hospital, which opened just shortly before the earthquake. And one looks at damage like this and you say, oh, look at that soft story. Wouldn't it have been great if we could have spread that inelasticity up the building? Also look at the damage to the columns and say, oh, we can actually design for deformation capacity if we confine those columns versus leaving them unconfined like the one on the left. It also shows us how health and safety has changed over the years. Wouldn't be approaching a building like that in such condition today. Well, nowadays, I think we recognize that things are a little bit more complex. And so our building design improvement cycle needs to expand a bit, right? We look at the performance and we need to consider the performance of the non-structural system. And really what becomes important are the bigger impacts. And I'm going to classify these into economic, environmental, and social. And I'll come back to those classifications in a second. And again, ERI LFE has been sort of central to this thought process. But what we asked ourselves afterwards, instead of how can we change the structural performance, we asked ourselves, what changes are necessary to manage future impacts? Okay, manage impacts from future earthquakes. So essentially, this is the process I want to go through a little bit here today. And so to start off with, let's talk a little bit about what impacts have been observed from recent events. And then we'll talk about what possible design changes we might make to manage those impacts. Notice I say manage, not eliminate, because eliminate would probably be unachievable in most cases, but manage. All right, so I'm going to pick an earthquake that I am intimately familiar with. I'm intimately familiar with this earthquake because on February 22nd, 2011, when it happened, I was standing right here in this dust cloud in the middle of Christchurch and watched a building partially collapse in front of my eyes. So it had a big impact on me in many different ways. You're probably familiar with some of these direct outcomes from the event. For New Zealand, this was a very large event in terms of fatalities, in terms of impact on the central business district. That's the downtown core. The downtown core was cordoned off for up to 2 years after the earthquake as they managed the damage in that area. Over 170,000 residential properties were damaged. Now, you got to remember here, standing here in the city of Mexico City with, what's the population of Mexico City? 18 million? 10. Oh, all right. So this is a city of 400,000. It's a small town. So that impact on the residential properties is massive, considering the size of the city. But what I want to focus on are more the indirect impacts, the wider impacts. And as I said, I'd like to classify these as being economic, environmental, or social. Okay? And all of these are different impacts, and some examples are shown here. And building performance has some relationship with all of these, okay? Some more than others, but some. Instead of reading through these, I'm going to just pull out a few to show you in a little bit more detail on the subsequent slides. So first, let's look at economic. So shown on the left here is the commercial office space in the downtown core of Christchurch. And this is the date of the earthquake when it dropped right down to zero. And in fact, you can say we lost essentially 75% of the office space in the downtown core. And that loss remained well beyond when that cordon that I just talked about was in place. So, and it took many, many years for it to get back up to the levels it was pre-earthquake. So significant impact of the loss of that office space on the economy. On the right here is tourist accommodation. New Zealand, I believe it's the second largest industry in New Zealand is tourism. A lot of that is Lord of the Rings tourism. But for Christchurch, this was a huge impact to lose 60% of its hotel capacity in blink of an eye. You can see it also shows that motels, these are just like the two-story small accommodation that you drive up to, those actually did quite well. Shows us the resilience of those smaller, typically wood frame construction. I was very happy about that because I stayed in many of those motels for the years following as I did reconnaissance work. So huge impacts to the tourism industry. Demolitions. A huge number of buildings in Christchurch were demolished following the earthquake. In this study, Kim showed that over 60% of the concrete buildings in the downtown core were demolished. This is likely closer, more like 70% now. But one of the things I want to highlight from this is the environmental impacts of such demolitions. I find it hard to engage with kilograms of carbon. I just don't know what that really means. So I put this in terms of the equivalent one-way flights between New York and Los Angeles. This is equivalent of about 500,000 one-way flights between New York and Los Angeles in terms of the carbon impact, the demolition of all of those buildings. That's a pretty big impact for a small city. And if we look at the statistics down here, these orange bars show you how many were demolished for a given damage ratio. What we see is that we're getting a lot of demolition even with really lightly damaged buildings. You say, oh, how can that happen? It should be the damage that's driving that demolition, right? Well, actually, the decisions around these demolitions is quite complex. And this was a master's student of mine who thought through what are the different things influencing the outcomes on these buildings. And essentially, it's influenced by not only the earthquake itself, but the condition of the building prior to the earthquake, the economics of the building for the owner prior to the earthquake, and then the condition of the overall neighborhood after the earthquake and whether or not the owner really wanted to be back in that area, whether you were in a cordon or not, and that either made it easier or harder to rebuild. And then you go into what I call this vortex of complexity. And there's lots of stuff going on here, and I could give you a whole another hour lecture just on these factors. But a really important piece in New Zealand was insurance. New Zealand is heavily insured. The vast majority of these buildings that were demolished in Christchurch had good insurance. And that may have contributed to that decision to demolish. But like I said, that's a whole nother hour lecture. But what I want to emphasize here is, in addition to this large number of demolitions, we still have a good number of unresolved cases. In fact, 5 years after the earthquake, the local newspaper identified what they called 45 barrier sites. These were sites that were barriers to the development, to the redevelopment, the revitalization of the city. And 10 years after, this had now gone down to 30, but still 30 buildings that are essentially left abandoned 10 years after. And some of them included some of these really bigger concrete buildings in the downtown core. And including this one up here, which is the most tagged building in the city, with issues of squatters in the building, and of course, associated social issues that result from such an abandoned building in the city. In fact, impacting the property value of the places around this building. And speaking of social impacts, there was a very interesting survey done for the years following the earthquake, where they asked for the people to reflect on what was impacting their everyday lives. Okay, and they gave them a whole list of questions. Does this impact your life? Does this impact your life? And rated this as a slight, moderate, or major negative impact. Okay, or none at all. And I don't expect you to read all of these on the bottom. I've gone through and sorted them such that all the red lines here indicate those aspects which are related to the building or housing damage. Okay? And all of these are those that have a moderate or major negative impact on the lives of the people of Christchurch. And what we see is that of all these cases that have a moderate or major negative impact, the building damage ones really rise to the top. They were really having the most negative influence on their lives, on their well-being. And while that came down with time after the earthquake, it never really went away. It sort of comes to a steady state, and the building damage issues still weigh heavy. Okay. Another form of well-being impact were the widespread injuries. We often think about, in design, we think about life safety, right? But actually, injuries are also a direct impact of the earthquake and impact people's lives and kind of ongoing well-being issues for the community. So this was a study done by Horsepool where they collected a really amazing data set on injuries after the earthquake. And from all different sources. And you can see that some of these are just moderate and can be dealt with at a community clinic, but many of the are serious or critical cases. Those serious or critical cases tended to be concentrated, of course, in structural impacts. Okay, so this reinforces the fact that we need to focus our efforts on the structural performance to protect people against those serious injuries. But very widespread moderate injuries across a lot of different causes. Okay, I've just tried to give you a snapshot of these various different impacts. And I've just I've shown you that they're complex. It's never from just one thing. And so just showing you some examples here and what are sort of the contributing factors to that impact. While there are many contributing factors, building damage does play a role in each and every one. Okay? And so now at this point, I want to sort of change gears and focus on how we might manage that building damage and then how that could help improve or manage, in turn, the impacts. Okay? So to do this, let me turn to the New Zealand Building Code. And I'm putting this in the context of the New Zealand Building Code, but it could very well be done according to any jurisdiction. We'll have similar sort of provisions. And the most common of these provisions, and that appears ubiquitous around the world, is to protect people from harm, from injury. And in the case here, it says injury and not fatality. That's because it's intended to protect people from injury, both fatal and non-fatal injury. Okay. But there's also an interesting objective in the New Zealand Building Code that says to safeguard people from loss of amenity. Okay? Loss of amenity. What does that mean? It's a bit of a strange term, perhaps. So it's actually defined within the building code as shown here. And if you read that, I think in today's language, we would probably say this is about building function. It's about preserving the ability of the building to support the people in that building. Okay? Now, in New Zealand, we try to achieve these objectives through design targets, where we design for an ultimate limit state and a serviceability limit state. Okay? That ultimate limit state is probably what you're used to designing for here. In the case of New Zealand, this is designing for a 1 in 500 year ground shaking. For serviceability limit state, it's a much lower ground motion, only a 1 in 25 year ground motion. So that's a pretty small earthquake. And we'll come back and talk about whether these are appropriate in a moment. While you have these two, the ULS, ultimate limit state, really governs the design of most buildings. So it's the serviceability limit state has limited impact on most ordinary buildings. The only thing it does to a large degree is to control the amount of ductility that we're allowed to consider in our design. Okay, so how do we relate these design targets and objectives with the impacts that we were talking about? So over on the left side, I'm showing you the impacts that we talked about in the Christchurch earthquake. And up at the top, I've shown the building code objectives. And really, it's these design targets of SLS that gives us the amenity, and that protects against some of the damage seen. And then we've got ULS protecting from injury and fatality, and that really protects against these big losses, serious injuries and fatalities. But there seems to be a gap here. These issues around waste, carbon costs, empty buildings, those really are not addressed. And that suggests that maybe we need another building code objective. Maybe it's something related to a climate change related objective. And I'm going to suggest to you that maybe that is an objective around enabling repair. Okay? And so for the rest of the talk, I'm going to go through each of these three and try to suggest ways in which we can assess how we design for each of these design targets, okay, including enable repair. I'm going to start down here at the most familiar space, the ULS, then I'll go up to talk about SLS, and I'll end with this enabling repair. I'm going to focus on what design loads and drift limits or deformation limits we might need for each of these. But again, like I said before, there are lots of other aspects of the design process that are as critical, if not more, than these particular limits. But this is a start. Okay, before I do, I want to talk a little bit about risk-targeted concepts, because I'll use this risk-targeted concept a few times in the next several slides. And so the traditional approach is to, the seismologists are going to give us a hazard curve for our location, right? And this tells us the level of shaking for different probabilities, right? And typically in New Zealand, we, as I said, we use 1 in 500 as our annual exceedance probability. So you read across at 1 in 500, and that gives you your design essay, right? But what if you have another location which has a different sort of hazard curve, but the same value at 1 in 500? Do you still use that same design essay? Is that appropriate? Are we missing something about the rest of the curve? Maybe we should consider that. So the risk-targeted approach says, well, I not only have a hazard curve, I also have a fragility curve that tells me the probability of damage in the building or collapse to the building for that given shaking intensity. Okay? And Sergio said I could have one equation. So I can integrate these two together and get an annual frequency of exceeding a damage limit state. Okay? And so if I do that for this hazard curve and fragility, I get some risk, right? And maybe it's a really big risk to begin with. And you say, oh, that seems too big. It's bigger than some risk target. We'll talk about what that target might be in a moment. And so I need to make my building a bit stronger, stiffer, so it's not so damaged. So to do that, I shift my fragility curve. See that? I move my fragility curve over, and that reduces the risk, essentially the area inside that curve. Okay? And you reduce the risk to the point that you meet some risk target, and you say, good enough. Okay? And then you have this fragility curve that represents your building that you want to design now. Now the question is what value do you design for? You don't design for the fragility curve. You have to design for a particular value. And so here in the US, it's traditional to say you design for the 10% value, and that gives you your SA to design for. Equivalent to that, you could say, we believe that we have some collapse margin ratio for our buildings. In other words, a ratio between the median value on that fragility and the value I design at. Okay? And so I can read from that median value back to the design value, and that's the value I choose and I put into the standard and we design for. Okay, so this is the basic risk-targeted concept, and it's implemented in the U.S. in ASC 7 to get their risk-targeted MCE values. We're considering this concept in New Zealand, but taking a slightly different approach. First of all, we say to ourselves, do we really have a single risk target? Defining what is tolerable or acceptable risk is incredibly difficult because it's a societal tolerance. And so really we figure we really can only define a range if we're lucky. And so, and the risk that we're really interested in is protecting life. So it should really be something about fatality risk. So we define an annual individual fatality rate risk of somewhere between 10 to the minus 6, 10 to the minus 5. I'll come to those numbers in a sec. That translates to collapse risks as shown here, up to about 0.5% in 50 years, which is considerably smaller than what's used in the IBC in the US. But in the New Zealand context, this feels honestly too high. Doesn't really feel like it's an acceptable collapse risk in the New Zealand context. Using this fatality risk has the advantage that we can compare this to other life risks, right? And in fact, this table here shows life risk thresholds that are used in different sectors in New Zealand. These are largely from land use planning sectors. And the first thing you see is that there's no clear boundary. It sort of varies all over the place. These are, don't worry about the details here, but these are all different sectors that have these tolerance levels identified. But if you look at these, and particularly those for like new development here, we tend to see that there's a tolerable range where below that range is generally acceptable. Above that range is sort of intolerable. And so maybe this is where we expect our building code to fall, to define that sort of tolerable range. Okay? And so this is how we chose that 10 to the minus 5, 10 to the minus 6 is looking at what sort of values are used elsewhere. And then we went to our that process that I described earlier, and we said, okay, what if we take that 1 in 500 year hazard and we consider the range of possible fragility curves that could result from a new building that is designed according to our code. It's not just one fragility, it's a range of fragilities. And when we consider that range of fragilities and we use that 1 in 500 year hazard, we get this sort of distribution of risk. And it's a different distribution of risk depending on where you are. So this is 4 cities in New Zealand. And it also depends on the site class and the period of the building, but I'm just showing you one example here. And if I put on top of that, that tolerable range I was just talking about on the previous slide, you see that actually we tend to fall within that tolerable range. So we said, okay, the 1 in 500 still seems to work fine for us. We've used a risk-informed approach now rather than a risk-targeted approach. We've used risk to inform our decision that 1 in 500 is our design ground motion for life safety. Okay, so that's all about life safety, about protecting life. So now let's move to SLS, the serviceability limit state, and talk about protecting function, maintaining function. But before I do that, I just want to acknowledge uncertainty in how we approach this. Okay, and this is just a diagram to illustrate that as the damage goes up in our structure, the uncertainty in estimating any particular risk metric, whether that's performance of the building or loss of function in this case, goes up, right? And so it kind of suggests that we want to look for a design target that comes before that uncertainty blows up on us, right? And so we don't necessarily want to directly target loss of function because there's all kinds of uncertainty involved there. Instead, we're going to target incipient damage. And I'll start by talking about structural damage, and then I'll talk about non-structural damage. Okay? So we're going to use incipient damage as a surrogate for a high confidence in continued function. Okay? We're not actually estimating whether we're continuing function, but we're using incipient damage and saying, well, this provides us confidence that we're going to still be able to continue function. We're going to define that based on sort of remaining essentially elastic, so a ductility of less than 1.25. And we're going to choose a risk target of 50% probability of exceeding that in 50 years. And you say 50%, that's pretty high. But we are just talking about damage. Okay, it's not life safety in this case. If we get it wrong, we get a little bit more damage. That's not the end of the world. So maybe using a 50% value is okay. But we could revisit that. If you didn't like 50, we could put something else in there. So we do the same process as before. But now we have a fragility that represents essentially elastic. And again, we can integrate these two and see, oh, actually, that annual risk is too high. And we can shift that fragility over and find until that risk gets down to our target level. Okay? And then we can read off the design value for that serviceability limit state. And it turns out that that happens to be about a 1 in 500 year ground motion. Okay? Sorry, 1 in 50 year ground motion. Remember before, our current standard uses a 1 in 25 year ground motion. So this is quite a bit more rare, a bit bigger event. But this number actually tends to hold regardless of the location in New Zealand. So that's convenient. We can just design for that 1 in 50 ground motion. Okay, So now we have an essay for that's targeted towards fatality risk, an essay design value that's targeted for damage, for functionality. So the question is which one governs? And so we can compare these two, right? Take the ratio of the ULS one to the SLS one. And if we look across New Zealand, what we find is that actually most, if you'll just look at the coloring of this map, most of the places have value less than 4. It just so happens that the ductility that we design for in New Zealand for a ductile building happens to be about 4. And so what that means is that, that actually in all of these locations, SLS is going to control the design of these buildings if we use that 1 in 50 year motion. And that's quite different than what we have right now. Remember I said that the ULS, the ultimate, typically governs. But this is actually consistent with where the industry seems to be going. There's been a lot of talk at recent conferences in New Zealand about the need to consider designing at service level and checking performance at ultimate, that this would maybe deal with some of the issues from Christchurch. So this study has sort of supported that outcome. And it's interesting now to reflect on other countries' experiences. And here I want to reflect on Japan, because in Japan, they do design for essentially a service level and then check for ultimate. Whereas in New Zealand, we design for the ULS currently and check SLS. And so I'm comparing 2 earthquakes here. The black one was Christchurch. The red one is the Kumamoto earthquake in Japan in 2016. And you can see it's quite a considerably strong earthquake, larger than Christchurch in most cases. But if you look over here on the right-hand side, the red ones is all Kumamoto, and you can see most of them have no damage at all. And sorry, these are all the modern, what I'm calling modern concrete buildings. So past the code where capacity design and things like that were implemented into the code. And while the buildings in Christchurch, sure, they met life safety. We saw very few in the severe and collapse categories. We did see a lot here in the damaged category. Okay, and so there's something suggesting that the approach in Japan maybe is contributing to these better outcomes. And in terms of the overall community outcome, it's vastly different. So this is Kumamoto several months after the earthquake, and unfortunately I don't have an aerial view, but I was there and it was really functioning like no earthquake had happened. Yes, there were some pockets of bad damage, but essentially the city was functioning. This is an aerial view of Christchurch about a year or so after the earthquake. And while you may not be familiar with Christchurch, you can take my word for it. All of these empty lots here used to be buildings. Those are all buildings that have been demolished. Since this picture was taken, many of the buildings that are in this picture have subsequently been demolished. So a big difference in terms of the outcomes. Is it all because of this? Surely not. There's more to it than that. But it seems to suggest that this change in approach might help us in changing the outcomes. Okay. All we've been talking about so far is strength. And in the words of Hardy Cross, professor from the University of Illinois, strength is essential, but otherwise unimportant. What really matters is drift. Okay? So now let's think about this continued function aspect, but in terms of the drift. What sort of drift limits should we apply for drift-sensitive, non-structural components to enable continued function? So to do this, I'm going to consider partition walls. And I could use different damage states. I'm going to use this DS2, which is essentially the damage state at which you would really start to do repairs. Damage state 1 is it's not too bad. Many of us have partitions in our homes that have a little bit of messiness to them, so you probably wouldn't even do anything with a DS1. So DS2 you would surely repair. So we want to set a risk target for this. And again, I'm going to use that 50% limit. So 50% probability of damage exceeding a DS2 in 50 years. And how do we do this? Well, we now need something in terms of drift, not acceleration. But typically, our hazard curves are given to us in terms of acceleration. So we need to convert that. So it's easy enough to convert SA to SD, spectral displacement. Then we need to convert that spectral displacement to an interstory drift, a maximum story drift over the height of the building, and we do that by assuming a deflected profile based on whether it's a wall building or a frame building. But that's easy enough. We can convert those hazard curves into drift hazard curves. And then we need to integrate, again, that drift hazard curve with the partition fragility, okay? And the first time we do that, we end up getting a higher risk than we wanted. So we got to do something about that. But we can't change the partition fragility. It is what it is, unless you choose a low damage partition. But I want to just use your run-of-the-mill partition. I don't want to pay for a special partition. So maybe I need to stiffen my structure to reduce the drifts. So you can do that, but what that's going to do is actually shift your hazard curve, right, as you stiffen the structure. Okay, and you stiffen the structure until you meet that target. Okay? Well, what this shows us, and again, we can do this for several locations, and we consistently end up getting this at the service level ground motion of 50 years, we end up seeing a drift limit of about 0.7%. Okay? If we had done this for DS1, we would have gotten 0.3%. That's pretty small. If we compare service drift limits used in other codes, the Los Angeles Tall Building Structural Design Council has a limit of 0.5% in 43 years. Japan has 0.5% in what amounts to approximately 50 years. They don't do it in a probabilistic sense, though. Chile has 0.3% under reduced forces. So given these numbers here and my 0.7 value here, I'd probably propose a simple number that one can always remember, 0.5% in 50 years. So using that as a drift target to control damage to the non-structural, drift-sensitive non-structural systems. Okay, so now we've got some means of dealing with protecting life and structural failure. We've got means to controlling damage and continuing function. Now let's talk about the really new part, which is enabling repair. To do this, the first thing I need to do is to give you a definition, because really anything is repairable if you throw enough money at it, okay? So the definition I'm going to use is that it's not requiring safety critical repairs to occupy the building post-event, okay? What do I mean by safety critical? I mean a safety critical repair is one that is needed to restore either the strength or the deformation capacity of the building and its components. Okay? So that's the definition I'm going to use. And I'm doing this partly to make sure that my repairs that I do to the structure to a structure that satisfy this would be relatively simple, okay, and fast to implement. So I want something like what's shown on the left here with a bunch of epoxy injection, rather than something like what's shown on the right here, which is really rebuilding the whole wall. This is a wall building in Chile after the earthquake in 2010. I also want to identify that you can still have a fair bit of damage with this definition. So you're unlikely to be fully functional. But by making sure that you don't have any safety critical damage, you would be safe to shelter in place. And that's why we say it's safe to occupy. Okay, and that's really critical so people have a place to be, a shelter after an event. I'm going to focus here on the structural system. I'll come back and talk very briefly about non-structural, but there's a whole piece of work that's needed around repairability in non-structural systems. Okay, so to do this, I want to propose some component-based repairability limits. So repairability limits for our components, our beams, our walls, our columns. And so essentially I'm asking myself, at what deformation demand will a component require a safety critical repair? Or, put in another way, when do the prior cycles from that damaging earthquake influence the strength or deformation capacity of the component? Okay? So with these questions in mind, let's look at some test data. For me, that's sort of the first place to go to think about any of these things. And there was a great set of tests done by Kawashima and Koyama back in the 1980s, where they constructed identical bridge columns and subjected them to different loading protocols. One loading protocol on the first one here with 10 cycles at each drift level, and the other one with 3 cycles at each drift level. And what you see in this is that up until you reach about the peak in the response, the two were very, very similar. In fact, even in their damage pattern, very, very similar. Okay? But once we got past that peak, things started to get different in the damage pattern, and you started to drop off more quickly with the 10 cycles. But really, the number of cycles up until that peak did not really influence the performance that we were seeing. So that suggests that the number of cycles prior to the peak really didn't matter to the performance afterwards. Okay, how about walls? Well, I had a graduate student at the University of Auckland who wanted to explore this for walls, so he did a few tests. One where he just applied your standard cyclic protocol, and the other one where he first put it through an earthquake recorded in Chile, which had lots of cycles, and then put it through that standard cyclic protocol. And essentially, the peak in the response or the onset of bar buckling was unaffected by that prior earthquake, by the input of that prior earthquake. So the number of prior cycles did not matter until bar buckling, which is essentially the peak strength, was achieved. Then, of course, my student wanted to prove me wrong and decided to do a test with 10 big cycles at 1.5% prior to this standard cyclic protocol. And yeah, that resulted in a bit of a change to and a bit of a degradation at an earlier drift. But this just simply emphasizes the uncertainty in the outcome and the need to account for those uncertainties in our process. Okay, but also recognizing this is a lot of cycles at 1.5%, a pretty large drift for a wall. All right. So this tends to suggest that maybe we can define a repairability limit. if we push, if this represents the backbone of a component, and that component experiences an earthquake, and that's the first earthquake, maybe the response is shown there in green, doesn't go past the peak quite yet, okay? And then that same component experiences another earthquake that then pushes it past the peak. But that green one hasn't really influenced the response except that it's decreased my stiffness, okay? But my strength and deformation capacity has remained the same even though I had that green earthquake before. And this poor unlucky building has another earthquake that pushes it again. Because the blue one pushed it past the peak, surely I've lost some strength from that, and I've lost some deformation capacity. And so the cycles after the peak are now likely going to influence my strength and deformation capacity. Really a simple concept that people have pointed to before. But really what this suggests to me is that the demand, if the demand in the damaging earthquake goes beyond delta V max, that is when you need those safety critical repairs. But if it hasn't, then you don't actually need those safety critical repairs. And so maybe this drift at V max can be used as our repairability limit. Okay? Okay. Well, you might say, hold on a second. Well, you said that you got to reduce stiffness from that first earthquake. Surely that's going to impact the performance in subsequent events. And you're putting this poor building through so many cycles. Surely you're going to, what about low cycle fatigue? Isn't that going to influence the performance in future earthquakes? All right, so let's take each of these very briefly, and I'll try to address them. So first, reduce stiffness. And I think this is the part in a presentation where you need a video. I think we all need to wake up a little bit, and I tend to do that with shake table test videos. So hopefully this will work. Oh. Oh, no. I don't want to show you that. Sorry, this is difficult to control the... I don't know if the person in the room can do it for me. No, it's just going to... Because I need to press the button. Can they control it there? Can they control it in the back? Now it's stuck. Just roll the cursor over the video. Sorry, I should have tried this before to make sure it works. I'll describe the video instead. It's not working. Too bad. Well, you'll have to watch me instead. So this is a 10-story test at eDefense that I was lucky enough to attend. eDefense is the largest shake table in the world in Japan. I watched this test, and it was a big test, building shakes. So I'm building, shaking, to about 2% drift, okay? And then they, and there was damage to the building. They went through the whole building, mapped out the damage, and then they subjected the building to the exact same earthquake again. Okay? And if I could play the video, I basically play the video twice as a joke, because the behavior in both of those
was basically exactly the same. The peak drift in both directions, this is showing the peak drift in run 1 and the peak drift in run 2 were basically the same. This had a wall in one direction and a frame in the other direction, almost identical. So that reduction in stiffness that came from that first test actually made no difference. And that might be surprising, but actually Santiago Pujol collected data on shake table tests from around the world, both single degree of freedoms and multi-degree of freedoms. And you can see that really they follow consistency, that there is limited increase in the drift in the second run relative to the first. The only difference, there's a few cases up here and a few other cases where you get higher drifts, but in those cases, there was degradation in the first run. So as long as you didn't go past the peak, right, the prior damage did not increase the drift demand as long as there was no degradation in the first run. Huh. Wow. So that reduction in stiffness didn't matter. How about low cycle fatigue? Well, low cycle fatigue is often explored with cyclic tests on bars. And is this a mouse? I don't have any more videos, so thank you for trying. Yeah, sure. So these are often done by putting bars in a machine and pulling and cycling back and forth, and you cycle them at the same strain until failure happens, right? And what happens during that test really depends upon the length of bar that's exposed, and you have to get down to about 4 dB before you really suppress any bar buckling that happens in these tests. And I'm interested in before bar buckling, right? Because we're looking at the behavior before we reach that peak or bar buckling. And so if we collect data for cases where S over dB was less than or equal to 4, they're sort of up along here. And this is relating the strain to the number of cycles to failure. Okay, so then you ask yourself, well, what is a reasonable limit on that strain value? And what is a reasonable limit on the number of cycles that one might experience in an earthquake? And on the strain value, I polled a whole bunch of friends who are doing concrete research. And we came up with a number of about 5%. And I'd love to discuss this further with Professor Rodriguez and Professor Alcacer, see what their number might be. But something like 5% seems about reasonable. Then we looked at the number of cycles that we get out of typical earthquakes. And for 2 earthquakes, one after the other, because we want this building to be safe in the next earthquake, right? And if we take the mean plus 1 standard deviation of that evaluation, we get about 30 cycles, equivalent cycles. And so most earthquakes are actually in this box here, which suggests that it's really only up in this far corner where you might start to get low cycle fatigue issues. So generally what this tells us is that low cycle fatigue is typically not going to be a concern for repair if buckling has not been observed. So with that, we've defined this repairability limit. I'm just going to modify it slightly to say drift at Vmax or bar buckling. Okay. Now let's use that as our repairability limit, see what sort of numbers we get for beams and walls. So this was work done by Tayo Pabola, collected database of beams, database of walls was collected by Abdullah and Wallace. And this is just showing the deformation at peak drift or at bar buckling for both of them. And you see the scatter that we might expect from tests. You see that for walls, it's dependent on axial load, which is represented by this lambda parameter. Before I move on, I always like to just give us some numbers to hold on to in our minds. So lower bound for the beams is about 2%. And the lower bound for most of the walls, which have more reasonable axial loads, is about 1.3%. Okay, so I'll just bear those numbers in mind as we move along here. Okay, but it's not just enough to figure out a repairability limit to put into a standard. We can't just simply think about these test data. We need to think about all of the sources of uncertainty that influence the behavior of the structure. Okay, and so here I'm looking at the uncertainty, yes, in the test data, but also uncertainty in the design and construction of the components. That influences my capacity, and then influence in the demand in terms of the modeling and the record-to-record variability that might influence the distribution on the demand side. And then those essentially represent or can be turned into these distributions. And effectively what we want to do is shift that demand distribution up to the point that we reach some target probability of exceeding our repairability limit. And once we reach that, then that median in demand, that's our limit for our rotation demand. Okay, and that's the one that we pull out and we use as our limit. Okay, I've already used up my one equation I was allowed to use, so I'm not going to show you equations. I'll just show you the result. Okay, and the result is just something like this. So it's a probability of being repairable versus the hinge rotation. Okay, over on the right side here is the walls. Over on the left side is the beams. The beam turned out to not be all that dependent on the S over dB as long as we were less than the 6S over dB. Whereas the walls were certainly dependent on axial load, so it has this term lambda. So what value do we use off here? Well, there you need that sort of societal expectations of performance. But I'm just going to pick a simple value of 80%. So I want an 80% chance or 80% confidence that I'm going to be repairable. And what limit is that? Well, it turns out that that's that 2% for beams that we looked at a moment ago, and 1.3% for a mid-axial load to mid-axial load wall. Okay? All right, so those provide us with limits for those components. But what does that mean in terms of the repairability of our buildings today? Okay, so we're going to take two buildings, one in New Zealand and one in US, just to make it international. One frame building in New Zealand and one wall building in the US. This one's a real building over here. This one was designed by an academic, so perhaps a little bit more fictitious, but still useful. We modeled these, and we picked these in part because we had some test data for both of them, so we could develop really good confidence in our models. And then any of you graduate students out there who are doing nonlinear analysis, you've probably heard of multiple stripe analysis as a way of assessing performance. Well, we also did a multiple stripe analysis by picking 30 ground motions for 500-year earthquake, 1,000-year earthquake, and a 2,500-year earthquake. Okay, and then recorded the peak interstory drift and the peak hinge rotation for the wall. Okay, and what we found is that if we put on there our limits, that 2% and 1.3%, we found that the frame only exceeded that limit at DBE, at our design basis, 25% of the time. Our wall was even better, only 15% of the time. And because this is like a performance-based assessment that I'm doing here, I'm pretty happy. I would have been happy with meeting the medians. So generally, this means that our current designs are really satisfying this repairability limit for the design basis earthquake. And so our current designs at the ground shaking that we use for design basis are already repairable. So this is not that far away. It's achievable. And if we compare the repairability performance and the collapse performance, and this is shown for that wall building, we can get that from the results I just showed you. We can get a fragility curve that shows when we require safety critical repair and collapse. And what's interesting here is that the building meets that 10% probability of collapse in the MCE, which is the target in the US codes. But it also, that same building has a 10% probability of requiring safety critical repairs in the DBE. So that seems to suggest that if we were to design for a 10% probability of requiring safety critical repairs in the DBE, maybe we would get the collapse performance we're looking for free. And we could design specifically for that repairability performance. We need further study here to see whether this holds for more building archetypes. But if it does, that is quite promising in my mind. And one of the reasons why that's really promising is it acknowledges the uncertainty in predicting collapse, right? Collapse is defined in our performance-based design approaches by whether or not components reach some limit way out here, okay? There's some DU value. What I'm suggesting is that maybe we should be targeting this value up here, but target it in the DBE, in the design basis, instead of in the MCE for collapse. And that's really nice when we think about the uncertainty in our analysis in reaching these states, right? The uncertainty in analysis goes way up once we get past this peak, once the components start degrading, okay? And by the time we're looking at collapse, our uncertainty in our analysis is large. So should we really be basing our designs at that level? It feels to me like basing our designs back here at this repairable damage level seems more tangible. And we get more benefits. We get benefits for climate change. This is a plot showing different levels of carbon, or carbon equivalents, due to a design level ground motion, okay? And you can see here the scale goes up to, what's that, 300,000, and then I've extended the scale way out here to 2 million, because this curve goes way out to 2 million. And what I'm showing on the y-axis is the probability of exceeding those different carbon levels, okay? And what this black curve is here, it's all that carbon due to demolition. Essentially, the probability of having demolition of a building after that design level earthquake results in a massive amount of carbon, okay? And if we can reduce that probability of demolition by designing for repairability, then we're really left with the damage due to non-structural, the damage to non-structural components that contributes to that carbon impact. Okay? And you're only left with this tiny sliver back here that's due to the structural damage. as long as you have removed this impact from the demolition. Okay, so we could get some really big benefits from a climate change perspective by designing for repairability. So what kind of changes does this have on our design approach if we go for enabling repair? Really, the design process doesn't change. But what does change is it forces the engineer to think about post-earthquake repair throughout the design process. Okay? And this is really important when thinking about the non-structural components installed in the building. In fact, we sometimes install non-structural components such that we can access important piping facilities within the building. Why shouldn't we have these kind of hatches so that we could access the structural components, so we could observe to see the damage state of those components after the earthquake to enable repair? Okay, so that's maybe one change that could be made to non-structural systems. But also, it would force us to think about non-structural systems that support repairability, and in so doing, support functionality and better continued functionality. Okay, last slide, or last couple of slides. I'm just going to pull all these different pieces together that we've talked about into a design framework. So we've talked about SLS, the serviceability, continued function. We've talked about protect life, ultimate limit state, and we've talked about enable repair. And I'm going to go through and put these on this chart here, and then think about whether I've met the objectives of the talk that I sort of laid out at the beginning. One was to recognize the inherent uncertainties in the seismic performance. And we did that by setting a risk target for each one of these, okay? And so all of them are defined in terms of probabilities. But we also wanted our implementation to be simple, and defining our design in terms of probabilities is not simple. So we needed to extract from that a design target, and we did that. We just extracted a design target for each one of these across the board. Okay? And these are actually very similar to what we do currently in New Zealand. And I recognize that in many parts of the world where there is not a serviceability limit state, that adding this is an additional complexity. And where deformations are not checked in the analysis, that's an additional complexity. But for New Zealand, these are actually already done in our design process. So there isn't that much more complexity. And actually, it's even simpler still when you recognize that most of the time, you get this ultimate limit state for free, because we showed that the serviceability limit state would typically govern. Okay? But you can't just design for serviceability. Of course, you need to provide the capacity design, the detailing that is going to give you that good performance at the ultimate limit state. Okay? But all of this has been done to try to manage those impacts that we observed from the Christchurch earthquake. Okay? And while it's very difficult, incredibly challenging to trace back, if we were to implement this, how would these reduce? Too much uncertainty there, I think. But certainly, we have built these with these impacts in mind. So I believe that implementing this process will help to manage these impacts in future earthquakes. So finally, I feel like what I've tried to illustrate for you here is that if we do a design based on a service level earthquake, while checking repair limits under a design level earthquake, it can provide a simple way of reducing our post-earthquake impacts and give us a high confidence that we're going to meet functionality in our collapse targets and even life cycle carbon targets. And we've seen that current designs are not really all that far off of being repairable already. And so it feels like it's time to start to change our focus from the ductility-based design that we've been using for very successfully, I might add, but we've been using for 40-some years, and move towards more of a repairability-based design. With that, thank you very much. Yeah. I don't see any. This is too high tech. In the meantime, any questions?
Hi, thank you for the presentation.
It's playing.
You mentioned earlier that in New Zealand there's very strong winds very commonly. I was wondering if that's combined with an earthquake, would that have an extra effect? Or is there done like research about that there, that when they get combined?
It's a great question. So in talking with the students earlier, I had indicated that Wellington, where I now live, is very windy. Can often get winds over 100 kilometers an hour. Where this becomes an issue is if you have an earthquake that has reduced the stiffness of the structure, then it may then result in a softer structure. And so in wind storms, you may see more movement of those structures. And specifically with regard to this slide, I do not address that, but there is some work being done to consider wind effects on a softened structure due to the earthquakes. The epoxy injection of reinforced concrete will restore some of its stiffness. And if it is, and wind will typically not further crack the structure. So with that epoxy injection, you should probably be able to recover most of the stiff you need for wind. But it is very possible that you could have more oscillation of buildings. But I don't think you're looking at a severe, like a safety issue. I think what you're looking at is a comfort issue.
Okay. Thank you.
Yeah. It would be best if you're able to put it in full screen.
Yeah, I think that in full screen it doesn't work, but...
All right, there you go. So it is just a video of a building shaking. So me doing this is really just as good. And as I said, I would play it again twice just to illustrate that the second time the building was shook, the behavior was basically exactly the same as the first time. You would not have been able to tell the difference if I played two different videos.
Thank you very much for this great presentation. Repairability maybe easier if we use some devices like dissipation devices and seismic isolation. How often are these kind of technologies used in New Zealand?
More and more, they are being used. But one of the objectives I had here was to show that even your conventional buildings can be repairable. Because my sense is that we don't achieve the community, the widespread community impacts, unless we influence the majority of buildings. And while there is an increase in the number of buildings using dissipation devices or base isolation, other forms of protective systems, it's still a relatively small percentage of the overall building inventory that's constructed. So for me, it was really important to see whether or not we could demonstrate the ability for conventional structures to be repairable.
Thank you.
Thank you, Dr. Ken. Those results are suitable for buildings with useful life greater than 50 years?
Sorry, say that again?
If those results that you have presented are suitable for buildings with a useful life greater than 50 years?
Yeah, so we also in New Zealand use a standard design life of 50 years. However, it is a bit of a figment of our imagination. Seldomly do buildings reach 50 years and get demolished. Most buildings are around much longer than 50 years. And so it's really, design life is really more of a metric that is used to put importance on buildings. And so what's more important perhaps is the use of the building. Whether you have large occupancy in the building or whether it's used for a critical facility. And there's been more and more talk, particularly in sort of the post-COVID environment, of where we recognized that the home is much more critical than the office. So it's that use of the building that is probably more important in terms of classifying it. And then yes, I think these principles still apply. What I was really talking about was your sort of conventional building. But for a building with, say, large occupancy, we often design for a slightly higher level because of the larger risk to life, right? Well, since we have framed our design level in terms of fatality risk, we can actually calculate what that increase should be in order to maintain a similar life safety risk target, okay? When you're talking about a post-disaster facility that needs to be functioning post-event, you can use some of those functionality targets, but you would change instead of a 50% probability of being functional in 50 years, you would make that like a 95% probability of being functional, or 5% of non-functional. So you can use these frameworks, but you would just change some of the inputs. Yep.
This is just it says, bueno, es un reconocimiento, we'll read it in Spanish, por impartir la conferencia de la ductilidad, la reparabilidad, evolución de las normas de diseño a raíz del sismo de Christchurch, celebrado el 10 de abril de 2023, firmado por nuestra directora, y aquí un pequeño obsequio del instituto para que te tomes un café. So you can drink your coffee.
Oh, very important.
Water, whatever So thank you very much. It's a pleasure to have you here, and we'll always like to have you more time. So the next time that you come, you spend a week or at least 2 days in Mexico City. So thank you very much.
Thank you.
Pues muchas gracias. Yo creo que sería para los capítulos, tomarse una fotografía con el doctor, if you don't mind to have a photo
course
of
not.
the
Yeah.
student chapters, members and presidents and vice presidents and the leaders of the chapters to take a photo with you.
Good.
¿Quién más? ¿Quiénes son miembros del capítulo?
Where
Los
up?
capítulos.
Let me take this.
No tómense la foto todos entonces, pues.